Hello everyone, my name is Athina Ioannou and the title of my research project is the analysis of structural failure of complex thin concrete shells. This research commenced during my third year of studies and will be developed further during the FEBS Research Summer Internship funded by the Doctoral Training Partnership and the University of Surrey. Today's presentation involves a brief introduction to the world of thin concrete shells, the methodology that I followed during my individual project, and the obtained numerical results and discussion. The future work that I intend to do during my summer internship is also mentioned. The buckling response of double-curved thin concrete shells has been the epicenter of many studies over the years. Despite the continuous research conducted regarding the buckling response of thin concrete shells, the influence of initial geometric imperfections on the buckling capacity of such shells and their relationship with flexible formwork is not yet established. Therefore, the aim of this research is to numerically assess the buckling behavior of a non-standard thin concrete shell inspired by the KnitCandela geometry. The main objectives of this study are to comprehend its buckling response and investigate the influence of initial geometric imperfections induced by fabrication on the buckling capacity of KnitCandela. Moving to the methodology I adapted in order to achieve the objectives of this study, the KnitCandela geometry was generated using Rhinoceros 6 and Grasshopper. The geometry of KnitCandela was then imported on both SAP 2000 and AutoCAD. During the preprocessor stage, a mesh consisting of 4,152 nodes was created. Textile reinforced concrete is the main structural material and is assumed to behave linearly elastic in both analyses of this study. Table 1 demonstrates the material properties assigned on SAP 2000. The thickness of the shell was selected based on the shell's ability to resist load combinations without achieving high slenderness. Therefore, a uniform value of 20 centimeters was selected both for the membrane and bending thickness of KnitCandela. The boundary conditions of KnitCandela were taken as fixed. And finally, Eurocode 6 was used to identify the main loads acting on KnitCandela during fabrication. Those are demonstrated in Table 2. Moving forward, linear elastic and linear buckling analysis were performed assuming a perfect geometry. I then performed a nonlinear static analysis considering P delta effects. The stiffness of the model established at the end of the nonlinear static analysis was considered when executed linear buckling analysis. By doing so, geometric nonlinearities were considered. Once both analyses were executed, an order of magnitude of the computational results was established in order to ensure that the results obtained are reasonable. In terms of the structural performance of KnitCandela, KnitCandela exhibited primarily compressive meridian and hoop membrane forces and stresses. Small tensile axial membrane forces and stresses also arise close to the critical points of inflection. The minimum bending moments are detected at the chest of KnitCandela, whilst the maximum bending moments are found close to the point of inflection. The bending moments detected on node 751 were large in magnitude, indicating a high bending stiffness. Therefore, a mixed stress state occurs. Moving to the buckling response of KnitCandela suffers localized buckling in a diamond-shaped pattern at node 751, therefore confirming the influence of increased bending stiffness of the shell. Additionally, the scatter between the critical buckling loads obtained by linear buckling and nonlinear buckling analysis is 12.67%, confirming the sensitivity of the shell against accidental geometric imperfections. It is imperative to note that the buckling behavior of KnitCandela, consisting of a less dense mesh of 1,044 nodes, was also executed. The buckling factors were found to be less than 0, indicating that the thin shell is inadequate to carry the applied pressure. Another parameter that was found to influence the buckling performance of the shell under investigation is the boundary conditions. Fixed boundary conditions promote the formation of locked-in stresses at the supports. Locked-in stresses at the supports have the ability to reduce the buckling strength of KnitCandela further. The main concluding remarks of this research study are the following. KnitCandela lies within the theory of thin shells. Additionally, the localized buckling response of KnitCandela depends on the bending stresses arising from abrupt changes in curvature. Geometric imperfections also influence the buckling strength of KnitCandela. But also, the buckling response of KnitCandela is greatly influenced by the size and face of the mesh and the boundary conditions. Now, moving to the future work that I intend to do during my summer internship, I aim to validate the numerical results of this study by developing and testing a small 3D printing mold. This will be achieved by using the Ultimaker 2 Plus Connect 3D printing machine and testing them structurally to assess whether the KnitCandela shell is sensitive against fabrication tolerances. Thank you for listening.